Hello, my name is Ivan. Welcome to the model simulation of robotic systems. And in this video, I will give you comments regarding the second practice task. So here we have the second practice task, which is all about open chain planar robot, which is controlled via different strategies. So we will consider different kind of ways how can you control an open kinematic chain. So I will start with the motivation. So 2R robot, planar robot with the 2 revolute joints is the most common example to consider robot dynamics. So it's relatively simple since it contains only 2 links, and it's just a very great example to consider different kind of control strategies. So here we'll start with the simple PID control, such as we don't need any model of a robot. Then we will compare it with the model-based position control. And then we will finish with the impedance control with the gravity compensation. So before I will start, I need to say that it is a first part of the second practice task. We can finish it only when we'll have a lecture about contact modeling. So because impedance control is used if we need to perform a contact with external object, with the environment. So since I didn't explain you yet what it is, we will consider impedance control only for the position tracking, but actually it is needed if we consider physical interaction. All right, so we will start with the position control. So we use position control when the robot is isolated, and it means that the interaction force need to be equal to 0, and the whole robot state depends only on kinematics, right? So let us consider this 2R robot. First of all, we can solve a direct kinematic task. So here is a trivial trigonometry to calculate the position of end effector. So it is position. We can write it in the matrix form. We can take a time derivative to calculate velocities. So here you can see the vector of angular velocity, and this matrix is called Jacobian, J. We can solve inverse dynamics. So it is a picture is taken from, by the way, the picture is taken from modern robotics book. If you want to get more details, you can consider reading this chapter about inverse kinematics. So if we want to solve inverse dynamics, and inverse is the one when we do have a desired position of end effector, and our task is to calculate the angular position, θ1 and θ2, we can do the following. First of all, we can remember the Cassian's law. So here, if we do want to calculate x squared plus y squared, it equals to the square of L1 plus L2 square minus 2 times L1 times L2 times cosinus of this angle beta. Then we can derive from here the magnitude for the value for the beta. We can do the same to calculate, the same we can apply cosinus law to calculate alpha, and we can calculate theta 1 and theta 2. We can calculate the right solution and the left solution, because there's two solutions when we consider inverse dynamics. Excuse me, inverse kinematics. All right, so we know the desired angles. Now let us consider an example before we can go further. Okay, so here, this is the MATLAB, and I will send you this archive so you can see here 3 examples. We will start with part 1. So we need to write down to open this RRPID control and run the whole system. Just press run. It's very convenient to use this live script. This is our 2R robot. We'll wait a little bit. Yeah, and it works. It just works. First of all, let us consider the model. So here, the model itself is pretty obvious. There's nothing new here. The only new here is the MATLAB function here. So, those one. So what is going on here? First of all, let us consider the first MATLAB function. So here it is a time clock. We're sending here as the input time. And here you have an equation here for the just a circle. It is the trajectory that we want to follow. We call it as the P-des, that state for the desired. So it's position desired. Then we consider the desired P, and we divide it on the X and Y. And we calculate the desired angles. So here we solve the inverse kinematics. So as you can see here is theta 1 and theta 2. In my MATLAB, I call it as Q1 and Q2. So here you can see the same equations. So argument are cosinus, then gamma, Q1, then your Q2. So it's pretty much the same equations as you can find here. For more details, once again, consider reading the whole chapter in the Modern Robotics book by Kevin Lynch and Frank. All right, so here we stated the desired trajectory. Here we solve the inverse dynamics. Here we solve the direct kinematics, but here you can see that this is not desired, it is actual one. So we send the desired one to the PID here. We send it with a plus as the desired one, and actual one that we get from the position sensor, we send it here. Yeah, we look at the difference, and the difference to the error we send to the PID. The PID calculate the tau, and the tau is sent to the joint, right? Okay, so once again, the desired position of end effector, inverse dynamics, desired one, direct kinematics, actual one. And this is just to get all data. All right, now let us consider the live script. So here, there's some titles, there's the parameters that I need. Here you can see the controller coefficients, and you can consider how huge it is. We'll consider why it is later. But actually, we can consider it right now because we do not consider any dynamics of a system. We do not know anything about the mass without any length. We don't know nothing. We know only the state, the actual state of each link, just angular positions, and that's it. So here we use it to run the model. And here you can see some plots. For example, here you can see the difference between the desired one and the actual one. And you can see that there is a gap between the actual and desired one, and you can make it lower. You can make it smaller if you will increase coefficients, but also you will get greater torque. So here you can see torque, here you can see the positions. And here you need to write down your conclusion. All right, so it is the first example of a system when you do not consider any model of the system. We didn't derive any dynamics. We just use the simple PID control, and we get the motion. And here we can write any trajectory that we want, and it will be able, the robot will be able to follow any trajectory here. All right, let us continue with dynamics. All right. So if we want to get more performance, more efficient controller, we need to consider dynamics. We need to consider kinetic energy, potential energy. We need to consider Lagrangian. Once again, if you want to get go deeper in the details and to have a recap, consider reading the chapter 8 about the dynamics open chain. And here we can have a very nice example with the same 2R robot with all needed data to derive all the kinetic potential energy, to derive the equation of motion. So everything regarding dynamics is here. All right, so Lagrangian, kinetic minus potential, you derive equation of motion, and you do this feedback linearization. What does it mean? If you have a model that looks like this, you can come up with a control law that looks like this. You can put this control law inside your model, and you will get something like this, that the desired, you can tell the system what the acceleration will be. So let us consider the particular example. So we can derive this equation of motion for the dynamic model. We know that the Q double dot equals to control law, and we can set this kind of control law. So here it is QA stands for the actual position, QD for the desired position. Those are velocities, and it is acceleration, and KV and KP is just a coefficient of our controller. So now let us consider the example. Another one. So I need to close it. So another. So close it. Clear to clean the workspace. CLC to clear command window. So I will open the second one, press run. So it is the same robot with the same task to follow the same trajectory, but now we use a model-based control. So here you can see that there is no PID. Here we send tau, which is calculated here. And if you go there, here, you will see those equations. So basically, you can see that tau equals to m times u plus c plus n. M is the inertia matrix, C is the Coriolis centrifugal matrix, N is the gravity forces, and tau is the torque. So U is the something that we consider the control signal. It is our desired acceleration, which is calculated down here. If we go there, you will find the equation that I write down here. It is the desired acceleration plus kv, desired velocity, actual velocity, desired position, actual position. And this is the coefficient of stiffness. And since we use in the model, we can see now that our coefficient of control, proportional, and velocity for the damping, pretty much low, because everything actually is it's all because of the model, because now our control is effective, because it know how much energy we need to steer the system, because it knows about the mass distribution. It knows about how much force it needs. All right. So everything here is the same. It is the desired position of the end effector. It is the inverse dynamics for the desired angular position. It is the direct kinematics with the actual angular position. So, and the whole difference is here. All right. I believe that here everything is clear. So if you need more data, you need to consider reading not the whole chapter, but the very beginning of this dynamics chapter. So just everything that is related to this initial example, illustrative example with the QR robot. And for the control, you can go here with all this linearization of feedback. All right, let us, we don't need to save it. We can go to the next example here with the impedance control. All right, so the impedance control is something which is needed if you consider interaction with environment. Here we can see the derivation. So if you apply a force to the end effector right here, and if you multiply with the velocity of this end effector, you will get power P. And it is, if you multiply the torque times angular velocity, you will get the same power. From kinematics, we know that the velocity equals to Jacobian times angular velocity. You can do this trick with the transposition, and from here you can get the equation for the torque. If you know your Jacobian from the kinematics, and if you know the force which is applied to the end effector, you can calculate tau. It is a force control, and impedance control starts here. For impedance, you can use this kind of equation, where P is the desired position, P is the actual position, V is the desired velocity of end effector, V is actual velocity of the end effector. K and D is the coefficients, proportional and derivative. From here, you can think about it like you have a virtual spring, which is connected to the end effector and to the desired point. Where do you want to be? And if there is a gap between the actual position and the point where you want, it's like there is a spring there with a damper, and it apply force to the end effector, such as it pull the arm next to the desired point. It is the whole idea. Okay, so let's dive in into the I didn't change here. Yeah, let us dive into the next third example. Or 3. Also, you need to just run it. So regarding the live script, so here is pretty much the same, but now here you can see the plots. Now you can see, yeah, we didn't take a look in the previous example, but you can do it by own. For example, here you can see the plot looks very nice actually. It is for the trajectory, it is for the angular of actual angular position of joints, and this is tau. The block. So here now we do not need any inverse dynamics. Excuse me, we do not need any inverse kinematics here. So what do we have here? So let us start from here. You see that the torque which is applied to each of the regular joint is the sum of two components, tau E1 and just tau1. Let's start from here. Tau1 and tau2, what it is. So you can see the block which is called dynamics, and actually it's just the M component from the previous example. So here there is no M, there is no inertia matrix, there is no Coriolis forces, they only gravity forces. So we do a gravity compensation here. So we deleted M matrix, C matrix, we just set here only N. That's it. So we send here actual position, we send here geometry and masses, right? What else? So here is the desired trajectory, the same. This one is the direct kinematics. Let me call it as direct kinematics. Let me save it. It is for the to send all the data to the workspace here, and this is our impedance. Let's consider what do we have here. So it is just two components from the vectors. It is the control parameters. This is the Jacobian. The Jacobian was derived here. This is the linear velocity, and this is the force and the tau. It is the same equations as you can see here. We compute tau. We sum them with the gravity compensation, and we get the taus to control the robot. All right. That's it with the elaborated examples that you will be provided. Next, I would like to discuss the mechanisms. So here you can see 3 problems. So basically, those all 2 links robots with a planar open kinematic 2 links robots, but they difference in respect in terms of types of joints. So here we can see a revolute joint and then prismatic one. Here you can see a prismatic and then a revolute and two prismatic joints. So there's three mechanisms, and here you can see three types of trajectories that need to be followed, or any other that you consider is more complex than this. And let's dive into the into the individual task. So here you can see your ISO number, and next to the ISO number you can see the type of linkages that you need to do, the trajectory that need to be followed, and control techniques. You can do any control techniques as you want it. So in this video, you saw I showed you PID control, but to do this PID control, you need to solve inverse dynamics task. Position-based control, but for this one you need to consider inverse dynamics and model. So I guess this one is the most complex. And then the final one is the impedance control. For the impedance control, actually, you don't need any model. You do this impedance and you just add gravity compensation, but it's going to work with even without gravity compensation, but it's not going to be very well. Okay, so you can do any of this as the one that I mentioned, or you can even do any other one, just get the trajectory. Regarding the trajectories, you will be provided with this little book, and here you can find all the equation for the trajectories that I gave you. So, for example, which one I picked? I guess this one. So here you can see the equations. All right, so also there is much more complex. If you want, you can do those if you wish. All right, let's what else? All right, and yeah, let's wrap it with the conclusion. So here we consider three types of control. I gave you explanation about the elaborated example that you will be provided, and your task to create the models of different kind of planar robots and to derive control and to implement the simulation, such as your robot follows those trajectories. And that's it with this video. Thank you for your attention. If you do have any problems, if you do not have any questions, you can write me in the mail using email or in the chat in the Telegram. Thank you.